Welcome back, students. So the purpose of this lecture is to prove one and only one theorem. Theorem 4.3.5. Let fn from u to r be a sequence of functions. Then the sequence of functions fn is uniformly convergent if and only if it is uniformly cauchy. And maybe before we go through the proof, let's describe its use. So what this says is if a sequence of functions is uniformly cauchy, then that sequence of functions is uniformly convergent. And it also says the converse. So here's how you can use that. So let's suppose that f sub n is a sequence of functions. Let's say it's even a continuous sequence of functions. So that's not how you spell continuous, but that's okay. A sequence of continuous functions. And let's suppose that you really want to know what the limit is, but you don't know what the limit is right now. You'd like the limit to exist. And shoot, be continuous. So if you want to do that, here's what you can do. You can just show that the sequence of functions f sub n is uniformly cauchy. Once you've done that, you'll automatically know by theorem 3.4.5 f sub n converges uniformly, so you know it has a limit. In fact, the uniform limit. Then, as f is the uniform limit of this sequence of functions f sub n, which are all continuous by assumption, you will know that f itself is continuous. So, for example, let's suppose you want to study f of x equal to the sum from k equals 0 to infinity of x to the k divided by k factorial. Now you might know without even thinking that, oh, that's the Taylor series for e to the x. But since we haven't even really defined e to the x, and in fact that's probably how you would want to define e to the x, well, we can't just say that. We don't even know off the bat that this thing exists. Well, if this thing means anything, it should be the limit as n goes to infinity of the sum from k equals 0 to infinity of x to the k divided by k factorial. Well, this is a sequence of functions. Here we see there's a function. In fact, it's a polynomial. K equals 0 to n. That's a polynomial. So it'll be continuous. It's a polynomial of degree n. So if I want to show that this limiting thing is continuous, here's one strategy. If I can show this sequence converges uniformly by showing that it's uniformly cauchy, I'll automatically know that the limit exists, and since it's the uniform limit of a sequence of continuous functions, it'll be continuous. Nice. So with that out of the way, let's actually prove this theorem. Uniformly convergent if and only if uniformly cauchy. And the proof, well, just like all of the other Cauchy, well, when we proved the Cauchy criterion for sequences of functions, there was one direction that was very easy. If you know that the limit exists, it'll be stupid easy to show that the sequence is uniformly cauchy. Right, so let's suppose f is, so here's the easy direction. Suppose that fn is uniformly convergent. Let f be the uniform limit. We're going to try to show that f sub n is uniformly cauchy. Well, here's what we know. We know that f sub n of x gets very close to f of x, provided little n is bigger than big N. Oh, but I also know f sub m of x will be very close to f of x, provided little m is bigger than big N. Well, they're the two things that I would like to show are close together. So if I could make this be epsilon over 2, and this side be epsilon over 2, then this length will be epsilon. At most, epsilon. So there we go. That's how the proof is going to go. Suppose that Fn is uniformly convergent. Let F be the uniform limit. Consider any epsilon bigger than 0. Since F is the uniform limit, it follows that there exists a big N such that for all x in U and for all n in big N, if little n is bigger than big N, then the absolute value of f sub n of x minus f of x is less than epsilon over 2. So except for the epsilon over 2, that's just the definition of uniform convergence. And I know that I want an epsilon over 2 at the end because of this picture. So now, consider any little m and little n bigger than big N. Consider any x in the domain U. Then, well, that picture tells me what I am supposed to add and subtract. The absolute value of f sub n of x minus f sub n of x is equal to the absolute value of f sub n of x minus f of x plus f of x minus f sub m of x by adding and subtracting f of x. That's the thing which I know is simultaneously close to f sub n of x and f sub m of x. By the triangle inequality, that's less than or equal to the absolute value of f sub n of x minus f of x plus the absolute value of f of x minus f sub m of x. Oh wait, so little n is bigger than big N. Right, little n is bigger than big N. That means I can use this implication. Little n is bigger than big N, so I know that that conclusion happens. So the absolute value of f sub n of x minus f of x, this piece, is less than epsilon over 2. But I also know that little m is bigger than big N. So, since little m is bigger than big N, then this same conclusion happens where n is replaced with m. So this piece is less than epsilon over 2. Epsilon over 2 plus epsilon over 2, that of course adds up to epsilon. So let's just look at what we did. We considered any epsilon bigger than 0. We used the assumption of uniform limit to come up with a choice of big N. We considered any m and n bigger than big N, and any x in the domain U, and concluded that absolute value of f sub n of x minus f sub m of x is less than epsilon. That's what it means to be uniformly cauchy. Now, on the other hand, suppose that f sub n is uniformly cauchy. We need to construct a uniform limit. And let me go ahead and sketch how the argument will go. So, here's how I'll go. F sub n uniformly cauchy implies f sub n pointwise cauchy. Right, we proved that, we just did. That in turn will imply f sub n pointwise convergent. Let's set f of x to be the pointwise limit. Well, it's also not hard to believe that if f is the uniform limit, then it's also the pointwise limit. So, this thing will be, here is the candidate to be the uniform limit. So how will we show that that is the uniform limit? Well, play some games with the definition of uniform cauchy and conclude that f sub n is in fact uniformly close to f. That's the game we'll play. So let's let's go for it. Let's suppose f sub n is uniformly cauchy by proposition 4.3.3. Uniform cauchy implies pointwise cauchy. So if I know that f sub n is uniformly cauchy, then f sub n is pointwise cauchy. And so, by theorem 4.3.4, the thing we just did, we conclude that f sub n is pointwise convergent. Let f from U to R be its pointwise limit. Then f is the thing that will be the candidate to be the uniform limit. I don't know that the uniform limit exists, but if it exists, it has to be f, So in order to show that it exists, I'll show that the limit is f. So now, what do I want to show? I want to show that f is in fact the uniform limit. So what do I want to show? I want to show that for all epsilon bigger than 0, there exists a choice of big N which does not depend on the choice of x, such that for all x in U, and for all n bigger than big N, absolute value of f sub n of x minus f of x is less than epsilon. Well, so let's get started. We'll consider any epsilon bigger than 0. Since f sub n is uniformly cauchy, there exists some big N such that for all m and n bigger than big N and all x in U, we will conclude that the absolute value of f sub n of x minus f sub m of x is less than, and I get to put whatever I want there. So let's try to figure out what I want to put there. So for all m and n bigger than this choice of big N that we've made, I know that the absolute value of f sub n of x minus f sub m of x is less than epsilon. So let's now, so I want something that has no m's but does have n's. So let's try to use that. So now that I've considered any m, I've gotten my choice of big N, let's fix some x in U. And what do I know? I know that f sub m of x goes to f of x as m gets big. So that means this quantity is getting really, really, really close to f of x. So let's take advantage of that. So let's rearrange this so I solve for, I don't know, f sub n. So if I take that and solve for f sub n, I'll get, well, we've done this enough times, f sub m of x minus epsilon less than or equal to, nope, strictly less than, f sub n of x less than f sub m of x plus epsilon. So let's take that and take the limit as m goes to infinity. So I'm not taking the limit as n goes to infinity, just as m goes to infinity. N will stay put. So what will I get on the left-hand side? I'll get f of x minus epsilon. The less than will just become a less than or equal to, but that's just the cost of doing business. F sub n of x less than f, less than or equal to f of x less than or equal to, emphasize, plus epsilon. So putting this all back together, I see minus epsilon is less than or equal to f sub n of x minus f of x less than or equal to epsilon. So absolute value of f sub n of x minus f of x is less than or equal to epsilon. That's not quite what I wanted though, right? I wanted a less than epsilon right here. So in order to fix that, well, what if I just want to replace all of these epsilons with epsilons over 2? Then I would get a strictly less than epsilon. So there's the plan. I'll write down the statement of uniform cauchiness. Then I'll take the limit as m goes to infinity and see what it says about f sub n. Cool. Solving this inequality, we for f sub m. All right, fine. No. I'm going to stick with my guns. You can solve for f sub m if you want. I'll solve for f sub n. Yeah. So I'll end up with f sub n of x in the middle. I'll get f sub m of x minus epsilon on one side, f sub m of x plus epsilon on the other. This is the downside of having these prepared notes. And I read them before I start. I wrote them myself. but there's more than one way to do a thing. Maybe that's an upside. I don't know. All right, so let's just take a look at this. F sub n converges to f of x as a sequence of real numbers parameterized by m. And right, all that that's using is pointwise convergence. I've fixed the value x. Now I'll take the limit. Passing to the... Oh, and those should be epsilons over 2, shouldn't they? Taking the limit as m goes to infinity, so n is going to stay put. I'll see that f sub nothing, f of x minus epsilon over 2, less than or equal to f sub n of x, less than or equal to f of x plus epsilon over 2, so that the absolute value of f sub n of x minus f of x is less than or equal to epsilon over 2, which in turn is strictly less than epsilon. And let's just summarize what happened, right? Because some complicated trickery happened, so we should probably check that this actually proves what we think it proves. So let's see. We considered any epsilon bigger than 0. We got a choice of big N. We got our choice of big N by just using the... Oh, nope. Down here. Suppose f sub n is uniformly cauchy. We considered any epsilon bigger than 0. Since the sequence is uniformly cauchy, we came up with a choice of big N. That big N happened to have an epsilon over 2 here. Maybe we could do better. In fact, we definitely could. We could do 2/3 of epsilon, but that's fine. We came up with a choice of big N. And we noticed that whenever little m and little n are bigger than big N, we can solve for little n. In particular, I want to emphasize we consider any little n bigger than big N here. So maybe I'll write the concluding sentence. Oh no, it's right there. Thus, for any epsilon, because we started with consider any epsilon bigger than 0, we've exhibited a choice of big N, so that for all little n bigger than big N, we also considered any little m bigger than big N, but that was part of the proof, not part of the conclusion. And any x in the domain, the absolute value of f sub n of x minus f of x is less than epsilon. That means f is the uniform limit of f sub n. Since f sub n has a uniform limit, it is uniformly convergent, as we claimed. Now I have some time, so I think I want to do one last thing. I want to talk a little bit about the homework, and you'll notice that the version that you see online does not have this sentence. That's because I do want to collect some of the homework on this. In order to help... So let's talk about what this homework is even asking you to do. It is not asking you to reproduce any of the stuff that we proved in class today. Instead, it's asking you to do applications. Applications of these theorems. So let's even just read through the first statement. Let a be bigger than 0. Let f sub n of x be the sum from k equals 0 to n of x to the k divided by k factorial. You'll notice that you recognize that as the nth Taylor polynomial of e to the x. Now, if you can prove that this sequence of functions is uniformly cauchy on the interval from negative a to a, then you'll conclude that it's uniformly convergent, so you can talk about its uniform limit. But then that uniform limit is the uniform limit of a sequence of continuous functions, and so is continuous. And then you can do the same thing with another function, x to the k divided by 2 to the k. What I'll do is, in the next video recording, is I'll go through a sample problem, which will be similar to these, in order to give you an idea of how to proceed.